So let's have a look at some basics of cryptography. So this is the first part of the presentations, and we're going to have a look at some basic private key encryption, and then we'll actually have a look at to see how safe our keys are. Before we do that though, let's have a look at some of the heroes of the computer security industry, and someone who has a great deal to say about security is Bruce Schneier. He's written many books and also developed the two-fish, blowfish cryptography codes and published books such as Secrets and Lies. Then we have the great Whitfield Diffie, and Whitfield Diffie was a person who came up with a key sharing scheme where two people could communicate openly and they would end up with the same key. So we'll have a look at that in part 2. Then we have Rivest, Shamir and Alderman, who came up with a public key encryption algorithm called RSA. Again, we'll have a look at that in a future presentation. Ron went on to develop important hashing functions, as we'll see in a later unit. And then we have someone like Phil Zinnemann, who decided that an email was insecure and also didn't prove someone's identity. So he came up with PGP encryption, which allowed users to be able to send secret emails. And finally, we have these two chaps who came up with the AES encryption method. Okay, so the first thing we're going to have a look at is some basics of the classifications of cryptography type. Okay, so first let's meet Bob, and this is Bob here. Okay, and then along with Bob we have Alice. So Alice is down here. Okay, let's draw her here, and here we have Alice. Okay, so it's our task to allow Bob and Alice to be able to communicate, and also for Bob to identify himself to Alice and vice versa. Unfortunately, we also get Eve, and here is Eve, and Eve is our clown. Okay, and unfortunately Eve wants to listen to the communications, she wants to be able to change the messages, she wants to pretend to be Bob to Alice, and so on. Okay, so let's look at the basic methods that we have within cryptography. First one that we have is that we use one key to take our plain text into ciphertext, and then back again. The same key is used on both sides, and this is called private key or symmetric encryption. So typical ones that we have are RC2, RC4, DES, 3DES, AES, and so on. The next method that we have and was developed by Rivest, Alderman and Shamir is our public key encryption. With public key encryption we have two keys. Those two keys are special. Once one key encrypts, only another special key will be able to decrypt that message, and it's called asymmetric encryption or public key encryption. Typical methods RSA, DSA, and it normally involves factorizing prime numbers. Okay, ElGaMo is another one that we get. It's called the elliptic curve method, and again we'll present that in another presentation. Okay, the next method that we have is a one-way function. With a one-way function we typically take a fingerprint of our data. It can be a whole lot of data or it can be a little bit of data, but we create a fixed sized hash signature, and we'll present this in a future unit. But typical hashing methods are MD5, SHA-1 and SHA-256. And finally we have a method which really isn't encryption but is a way to encode. With this we take a message such as hello, we then encode it into something like base 64, hexadecimal and so on. and that becomes our basic encoding. It's fairly easy to be able to decode that because it's easy to know the code. Okay, so first let's look at how we convert our plain text into some ciphertext. Okay, so let's bring Bob back again, and let's draw Bob with his little computer here. Okay, that's Bob. So Bob has a whole lot of characters. We call some plain text, and that plain text is represented with ones and zeros. So computers really only understand ones and zeros, and what we're going to do is encrypt these. So one standard that we use is to be able to use ASCII. So ASCII is a standard code that we use around the world to be able to represent text in the series of ones and zeros. So for example, big A is 01000001 or 41 hexadecimal. A little a is 01100001 or 61 in hexadecimal. Okay, so that's how our values are stored or transmitted. Then we can encrypt and we convert it into ciphertext. So here's our ciphertext here with all ones and zeros. It can be quite difficult for us to be able to interpret this as humans. So as humans we represent it in a different way. We either represent it into hexadecimal. We take 8 bits at a time and we convert them into base 16 or into base 64. So both of these values are the same, are different representations of the same bit value. Okay, so this is our ciphertext here. And base 64 hex are used to convert from our binary into readable characters. So this is the conversion that we have for hexadecimal. So with hexadecimal we take 4 bits at a time and we convert each of the 4 bits into a hexadecimal value. So we can see that 0 represents our hex digit of 0, a decimal of 10 is an A, and a 15 is an F. So all we need to do is to remember to count up to 15 and we're okay. Base 64 is slightly different in that we take 6 bits at a time and then we look up the value for the 6 bits and we convert that into a base 64 character. In this way we can represent a binary stream in terms of standard character sets. Okay, so the first method that we'll have a look at in this presentation is private key encryption. It's otherwise known as symmetric key encryption. We only use one key. So let's bring Bob back, and where's Alice? There's Alice there. Okay, so Bob really wants to send a message to Alice. Okay, so what he does is he draws his key. So he brings up a key, and this is his private key. So he might use from a standard method such as AES, D3DES, 2fish, and so on. So what he must do now is take his message. So hello Alice, how are you? Okay, and then converts that into some ciphertext. Okay, then he's going to send that over to Alice. Okay, thank you. Alice says she's received it. Okay, now how does Alice decode or decrypt the message? Well, what she needs is the key from Bob. She gets the key from Bob, okay, and then she'll unlock the ciphertext and she reads the message. That's perfect. Unfortunately, as we've seen, we have Eve. So Eve is actually sitting looking at the communications. So the problem that we have is four questions. What if Eve is listening to the key that's been transmitted? So we've seen that Bob sent over the key to Alice. Eve could have been listening to that. She now has a copy of that key. Okay, so she's listening, she has a copy of it. Next question is, how does Alice know it was really Bob who sent it? Because now that Eve has the key, she could really be Bob and encrypt the messages. The next question is that how does Alice know that Eve hasn't modified the message in its transmission? And the final question that we ask is, could Eve try lots of keys and actually brute force it? So even though she hasn't been able to listen to the keys, is it possible for her to take the cipher text and then try lots of keys to be able to brute force the key that Bob used? Hopefully we'll answer all of those questions in the next few presentations. So first, let's look at key size and see how secure our keys actually are. So let's draw our key. Okay, so this is a special key. This key has 4 notches in it. The notches can either exist or not exist. Okay, so they can't be different sizes of notches. They're just there or they're not. So the first question that we're going to ask is that if we had a key that we built like this, how many keys are possible with our 4 notches if we were to manufacture this? Okay, so I'll just give you a minute to think about that. Is it 4? Is it 44? Is it 4 million? Well, it's actually 16, or 2 to the power of 4. 16 different keys. If we have n notches, or n bits, then we have 2 to the power of n keys. And here are our keys being delivered to us. Thank you. And there they are, in binary. So there's one without any notches, 0, 0, 0, 0, and there's one at the very end with all ones, 16. So just think, if we were to create ones with 64 notches or 64 bits, and let's say we created our keys, each of them were 1 millimeter. How many keys do you think, how many keys would we need, and how long would that be if we laid them all end to end? The width of the campus at Napier, the width of Edinburgh, from here to the moon, the width of the solar system, or the width of the Milky Way? Well, actually, that's a lot of keys, and it would actually be larger than the Milky Way. So you can see that we actually have quite a lot of keys if we're using the 64-bit encryption. Okay, so let's see how they can be cracked. Well, one method is with brute force. With brute force, Eve, here we have Bob, and Alice again, and in this case we have our plain text. That's going to be converted to our cipher text. Then Bob creates his key, and then we have Eve. Alice should have the same key if we're using private key or symmetric encryption. So there's our cipher. Okay, hello, how are you? That's converted into our cipher text. So all that Eve does is she creates lots of keys, keeps trying the keys, keeps trying them, and then she does a quick calculation to see what the decoding is. First 2 there are wrong, but there we go. At the very end, she's found the right key. So through brute force, she's managed to try all the keys and then has managed to find one which actually works. Bit like when you have lots of keys for your door and you're trying to find the one that fits, and eventually you get to it. You don't have to try all the keys, Sometimes you might have to. Sometimes you might get lucky and get the first key. But on average, it'll take you half the key space to be able to find the key. So if we think in terms of our electronic keys, this is what we get. So for a 4-bit, there we go, 16 keys. For a 32-bit, we have 4.29 times 10 to the 9, 4 billion keys possible, and then it keeps going up. Okay, so every bit that we add to our key, we make it twice as difficult to crack. Okay, so let's look at how long it's going to take us to be able to crack through brute force. Okay, so let's take an example. Let's say a 64-bit key. It's 1.84 with 19 zeros. Okay, that's 18.4 million keys. It's a lot of keys. How long will it take us on average? So let's say we'll take a fairly average type computer. Okay, we'll take something that will crack a billion keys in a second. And then we'll do a calculation. Okay, let's do our calculation. So if we calculate that, then with the 1 nanosecond clock that we've got, it'll take about 9 billion seconds, or 285 years, on average, to actually crack a 64-bit key. Okay, that's quite a long time, and probably you would have to be a king sending a message to be able to send, for the message to be able to be cracked. Okay, so but we know that computers actually get better every year, and computers that we use now are not very powerful after even just a year or so. So there we go. If it took us 285 years this year, then next year we'll say that, let's say the computing power doubles. It's only going to take us 143 years. Still seems a long time. But let's continue on, and let's see where we get to after a few years. So we can see after 18 years, then it takes us 1 day. Okay, with just 18 years from now, something that took us 285 years to crack, we can crack in 1 day. And we can see we have a whole lot of devices now that could probably crack these types of keys if we wanted. And we need to worry because DES, which is the standard in 1975 used in the finance industry, was developed 40 years ago, and it's now easily crackable, probably even by a mobile phone itself. And the other thing we can do is that we can create arrays of computers. So we can have a network of 2 or 4 or 8 or 16 all connected together. And then with encryption, what we can do is that we can share the keys across, say, 2 computers. So we're now halving the key space. Half the keys go to one computer, half to the other. And we can do the same. If we had 4 computers, we could quarter the key space onto each machine, and we could keep scaling up from there until we created a massively parallel computer system. If we look at in terms of time, and also with the computing power increasing, also in terms of the number of processors, look what happens. So with 1,040,000 odd processors, just after 1 year it's only taken us 1 hour to be able to decode that. So computing power increases, and the number of processors that we can get access to can also increase. And there we go. We can see here our 64-bit key, which took 284 years, is cracked in less than an hour. And this was shown by this machine here in 1998 when the Electronic Frontier Foundation searched for 90 million keys per second with these parallel chips here, and it took them 2.5 days to be able to crack DES, just to show that there was flaws in this 56-bit DES. These days we can get this device here, a Copacabana machine. It's massively parallel. And it takes about 9 days for a 64-bit DES to be cracked, and it costs less than $10,000. So we can see that that these machines are getting much more powerful and can parallelize the computation. So let's have a look at the current state of the art in cracking, and we'll have a look at a little bit of history. So he didn't do it, but in 1997, around that time when he was around, the RSA Labs distributed a 56-bit RC5 encryption challenge, and the distribute.net, which we'll see in a minute, that's their logo there, they cracked it in 250 days, and they searched about half of the code space, the key space, 47%, and actually found it. Then when the Scottish Parliament was being created, the RSA Labs had another challenge in 1998, and they were cracked within 39 days, 25 days, and so on. At the start of the millennium, again, there was another challenge, DES 3, and it was cracked within inside 22.5 hours using this deep crack custom DES cracker. Then 2002, RSA Lab had a 64-bit competition, and this time it took 1757 days, 83% of the key space, so 64-bit was cracked. So where really are we now? Well, Distributed.net has now taken over the challenges, and we're at 72 bits. That's the state of the art in terms of this type of encryption. So anything up over 72 bits is fairly secure in terms of private key encryption. So where we are just now is that we have about 94,000 participants taking part in the challenge, 5,000 teams, and they've been searching for about over 4,000 days, and they've searched 3% of the key space, and they are searching about 452 billion keys per second. So that's quite a lot of keys that they're searching through. And the number of keys they're looking for is that's an awful lot of keys to search through, but they'll do it and they'll get there. More participants, the more chance they have to actually crack these codes. So the way they do it is that you download a screensaver, you install it, and then what will happen is that when the screensaver goes on, then it will search the some keys within inside the key space. So here we are here. We'll actually just show you what the screensaver looks like. And the peaks there are actually when the screensaver comes on. So you see the peak going up there, that's when the keys are being searched for, and then we go off screensaver, then back on again. So some of the major computers there are, supercomputers, one of the most powerful is called Titan, and the specification for Titan is this. It's a Cray XK7 supercomputer at Oak Ridge National Laboratory. It has over 18,000 CPUs, AMD CPUs, and also 18,000 of these GPU cards in it. And it runs about 7 terabytes of memory with a speed of 27 petaflops. Total cost, unfortunately, is $945 million. That's a lot of it's an expensive computer. And the other state of the art that we have is the Blue Gene IBM manufactured machine from Lawrence Livermore National Laboratory. It has Power PCs in it, 64-bit ones, about 32 terabytes of memory, 20 petaflops, and it has over 131,000 CPUs. And roughly, if we think about it, it's about 1.8 million times faster than a standard PC. Okay, so that's given us our basic presentation. I hope you can follow on to the second presentation.